Hey everyone. So in today's session, we are going to talk about logistic regression. In the previous one, we talked about linear regression, which was a regression model. Whereas logistic regression, though the term says regression, it's not regression, it's actually classification model. So logistic regression is one of the basic and popular algorithms to solve classification problems. It's a linear model. And as we already know, regression and classification both are supervised learning techniques. So logistic regression is also a supervised machine learning algorithm, and it can be used to model the probability of a certain class or event. So what does that mean? Let's say we have some x and then we have our y. X is basically your marks 56, 64, 73, 32, and y is basically whether you are placed or not. So 1 0 1 0. So this is the data that we have. I'm just restricting myself for this example to one independent attribute only. Now what will logistic regression do? Logistic regression based on your x value, let's say 64, 32, 81, it is going to model the probability of a certain class or event. So it's going to basically give you the probability. Let's say we get the probability of a class of a object being in class 1. That is the probability of a person being placed. So the probability is, let's say, zero point 0.6. Here it is zero point 0.3. Here it is zero point 0.8, something like this. So if you see, logistic regression will give the probability of a particular point being in a particular class. So when I say that logistic regression is giving the probability as zero point 0.6 of a point being in class 1, that means if x is 64, for this particular data point, x is equals to 64, the probability that we get from logistic regression is zero point 0.6, and this is the probability of this point being in class 1. And then what will be the probability of this point being in class 0? So this is the probability of class 1. Then what would be the probability of class 0? There are only two classes, 1 and 0 in our case, right? So the probability of this point being in class 0 would be zero point 0.4. Then what's the probability of this point being in class 0? For class 1, the probability is zero point 0.3. So the probability of being in class 0 will be zero point 0.7 because the total has to be 1. Then for this point, the probability of it being in class 0 is zero point 0.2. Okay. So generally what do we discuss is the probability of the data point being in class 1. For class 0, it is just 1 minus the probability of the point being in class 1. And here we are only talking about two classes. So basically this is called binary classification. That is, there are only two classes available with us, 1 and 0. Okay, and what is logistic regression doing? It is basically finding the probability of a particular point or a testing point of being in class 1, probability of it being in class 1, and also the probability of being it in class 0. Okay, we can have multi-class as well. Multi-class means that is there are multiple categories, there are multiple unique values in y. So we have x and we have y. Okay, so 64, 32, 81, 95, these are the marks, and the grades that are there are A, C, B, A, and so on. Okay, let me say this as B as well. Okay, like this. Okay, so let's say now we have new points. So this was the training data, and here also this was the training data, this was the testing data. So on this training data, we have built the model. So our model is ready, and we have the logistic regression model available to us. Now for the new points, we basically find out the probability of it being in class A, then probability of it being in class B, and probability of it being in class C. So basically, logistic regression will tell us what is the probability of it being in class A, that is of getting grade A. Then logistic regression will also tell us what is the probability of it being in class B and the probability of it being in class C. So let's say this is zero point 0.3, this is zero point 0.4. So what would be the probability of C? The total has to be 1. So zero point 0.3 plus zero point 0.4 plus zero point 0.3. Then here, let's say this is zero point 0.2, this is zero point 0.1. So what would be the probability here? It's going to be 0.7 because the total has to be 1. And here 0.25, 0.35. So here it is going to be 0.4. Okay. So if we know the two probabilities, then we can figure out the third probability. And logistic regression itself will give us all the three probabilities. So when we build the logistic regression model, we'll see that for all the testing points, it is giving us the probability of that point being in each category or in each class. Okay. So that's what logistic regression does. It basically models the probability of a event. Okay. Logistic regression is all about probabilities. Now, the next question is, why is it called logistic regression? The answer to it is that the underlying technique that is used inside logistic regression is actually that of linear regression. The mathematics of logistic regression is closely derived from the mathematics of linear regression. So that's why logistic regression, though it is classification, it is termed as regression. Okay. Now, we built our logistic regression model on this training data and we tested it here, right? Now we are giving the probabilities. We are giving the probabilities. So for this 0.64 being in class 1, the probability is 0.6 and the probability of it being in class 0 is 0.4. Now we'll also set up a threshold. Let's say the threshold is 0.5. Any value greater than equals to threshold in probability of class 1, it will be treated as category 1, and any value less than 0.5 will be treated as category 0. We can put the threshold on probability of class 0 also. That's also absolutely fine. So if we set the threshold to be 0.5, any value which is greater than 0.5 or equals to 0.5 will be predicted as 1, that is placed, and any value less than 0.5 will be predicted as 0. Similarly here. So these are the final predictions that we get, and now we can compare it with what the original predictions, the y actuals are here. Okay, and then how do we compare that? We are going to discuss it, but I just want to explain the concept of threshold right now. Any value which is greater than equal to the threshold will be treated as 1, and any value less than it will be treated as 0. We are doing this for class 1, right? We can set the threshold for class 0 also. That's also fine. Yes. So now let's move ahead and see the different types of logistic regression that are available. So the first one is simple logistic regression, and the second one is multiple logistic regression. So in simple logistic regression, what happens? We have just one independent attribute and one target attribute. And in multiple logistic regression, what happens? We have multiple independent attributes and then there is one target attribute. So that is called multiple logistic regression. This is very similar to what we did in linear regression, also the simple linear regression and multiple linear regression. Okay, now basically let's try to see if we can use linear regression for our classification. So this is something that we discussed. This is also something that we discussed. Now let's move here. So let us try to see if we can use linear regression to solve a binary class classification problem. Obviously, classification can be either binary class or there could be multiple class, but we are restricting ourselves to binary class here. Okay. So we have the data points like this. So there are multiple data points here. So X is basically our independent attribute and Y is our dependent attribute, and Y can only be 0 or 1. Okay, because there are two classes 0 or 1. So we have multiple points here, and for all of them, the class is 0, and we have multiple points here, all of them, the class is 1. Okay, so this is how the points are there. Now let's say we draw a linear regression line. So basically, we see this data and we try to figure out what would be the best fit line for these points, and this is the line that we come up with. So how have we got this linear regression line? Basically, the linear regression line is figured out by minimizing the sum of square of errors, right? So basically, this is the line that we got after we minimized our error function. But what's the problem here? Let's try to see what's the problem. Why can't we use linear regression here? We tried building a linear regression model. Is there any problem or are we good? For point x1, if you see, for point x1, if we come here, basically what we are predicting is 0.2. And let's say if we have set the threshold as 0.5, then since 0.2 is less than 0.5, it is being treated as class 0 only. Because if the threshold is 0.5, any value less than the threshold will be treated as class 0, and any value greater than or equal to the threshold will be treated as class 1. So for this point x1, we are also making the prediction as category 0, and the actual value is also category 0. So yes, we are doing it correctly here. For the next point, if you see x2, for x2, the prediction that we get is the probability that we get is 0.6. And since it's greater than the threshold we have set here is 0.5. You can change the threshold as well. So now, since it's greater than the threshold, it will be treated as category 1. So the prediction is also category 1 and the actual is also category 1. So for x1 and x2, our linear regression model is doing correct things. But if you talk about x3, this is your x3. For this, we are going to get our y or probability to be greater than 1. Can probability be greater than 1? No, it cannot be. Obviously, for this value, let's say it's 1.5, obviously since it's greater than the threshold, it will be predicted as 1, but the probability cannot be 1.5. That's the problem. Our logistic regression models the probability, but the probability is 1.5, which is not possible. So our linear regression model is not able to perform well for x3. It's giving incorrect probability. Similarly for x4. If you see x4, the probability will turn out to be negative. Say, let's say minus 0.5. Now here again, the probability cannot be negative. Again, since it's less than the threshold, it will be treated as category 0, which is fine. But it does not model the correct probability. So linear regression is not helping us model the right probabilities. So that's why we need to modify our linear regression in such a way that always our answers are between 0 and 1 only, because the probability is between 0 and 1 only, 0 and 1 included. Okay. Now let's say we have outliers. What happens when there are outliers as well? So when we have one outlier, so instead of this L1 line, because of this outlier, your linear regression line is going to change and it will, let's say, become this L2, this brown line. Now, if you see this brown line and if you see, let's say, this point. So if you see for this point, it is turning out to be a value less than 0.5, which is, let's say, 0.4. So basically for this, what we are going to classify this point as, since it's less than the threshold, it will be classified as category 0. But actually, if you see, it is category 1. So it is predicted as category 0, but it is actually category 1. So for these points, so there are some points for which the classifications would go wrong if we have outliers. So basically, the error increases whenever there are outliers. Okay. So whenever we are having outliers, using linear regression will be a problem, and we'll have misclassifications happening for this binary classification. So there are two limitations of using a linear regression model for classification problems. The first is that the predicted value may exceed the range 0 to 1, and we want to model the probability. So basically, we want our answers to be between 0 and 1 only. And also the error or the misclassification rate is going to increase if the data would have outliers. So these are the limitations that linear regression will have for classification. And that's why we try to modify our linear regression to make it logistic regression to ensure that our values are always between 0 and 1. Okay, so let's try to do a bit of manipulations and try to convert our linear regression, which has these limitations, into logistic regression, where our answers will always be between 0 and 1. So this is our linear regression model. Obviously, yeah, our W0 could be anything, W1 could be anything, and X could be anything. So our Y will also be anything. So basically, what we want our Y to be is the probability, which is always between 0 and 1, which right now is not possible. The reason is W0 plus W1X could be any value. It's not that it's always going to be between 0 and 1. No. Now, the right side of the equation, this, can hold any value which exceeds 0 to 1 range as well, right? So, can we modify our LHS in such a way we cannot restrict our W0 plus W1X to always be between 0 and 1? We can but modify our LHS in such a way that LHS can exceed 0 to 1 range, but probability cannot exceed the range. So we cannot restrict this. This could be anything. So what we will do is, instead of writing P here, let's write something else so that our LHS can have any range. But our P, that is the probability, will only have the range 0 to 1. That is what I'm saying is, try to, instead of writing P here, try to write something else. And that something else is basically called odds of probability. So what does odds of probability mean? It's the ratio of the probability of an event occurring to the probability of the event not occurring. So odds basically means P by 1 minus P. Probability of the event occurring divided by the probability of the event not occurring. So if the probability of the event is P, the probability of the event not occurring would be 1 minus P. So that's what is called odds. And I am saying that instead of writing P in the LHS, write P by 1 minus P. What would be the help that this gives us? Okay. So if you see, P by 1 minus P could be anything. Let's say 8. But now if you try to figure out what is your P by solving this equation, your probability is less than 1. No matter what your P by 1 minus P is, your probability is less than 1. Let's try to take another big example also. P by 1 minus P, and it's a very big value, say 1000. Then again, let's try to do it. So what do we see here? We see that the probability is less than 1, no matter what our P by 1 minus P is. We can't restrict our W0 plus W1X. We can't restrict our W0 plus W1X, but we can restrict our P. So W plus W1X, W0 plus W1X could be anything. Similarly, P by 1 minus P could be anything. But our P will be between 0 and 1. So are we done? Like, is this the solution? Or we are missing out something? Will this always work? Will we always have our P to be between 0 and 1, where 0 and 1 are included? Is there any possibility in which our P would turn out to be not in the range 0 to 1? Can you think of it? There is a possibility. Let's say W0 plus W1X is negative, say minus 2. Then let's try to solve it. Minus 2 into 1 minus P. So this would be minus 2 plus 2P. So it would be P minus 2P, which is minus 2. It will be minus P is equals to minus 2. P is equals to 2. This is not possible. This is not possible, right? Our probability should be in the range 0 to 1. Let's see another example like this. So minus 6 plus 6p, then we'll have p minus 6p is minus 6. So minus 5p is minus 6, p is 6 by 5. So again, our probability is turning out to be greater than 1. So this is not the right probability. So that means p by 1 minus p will work when w0 plus w1x is positive, but when it is negative, it's not going to work. So we have to modify our LHS in such a way that this p by 1 minus p is always and always positive. How can we do that? And w0 plus w1x could be anything, but we want our p by 1 minus p to always be positive. So let's see. We have a function ln x. So if you see ln x looks like this, that is your ln x could be positive or negative, but your x is always positive. So if we could have instead of x p by 1 minus p, that means your ln p by 1 minus p could be anything, but your p by 1 minus p will always be positive. It cannot go in the negative direction. So if I write like this, that means your w0 plus w1x could be anything, could be any value, but your p by 1 minus p will always be positive. And when it will always be positive, then our probability will always be in the range 0 to 1. So that's what we will do. So the LHS, we have modified it to be ln p by 1 minus p. And here we have w0 plus w1x. Okay. Now let's just try to do a bit of mathematical manipulation to get it in a right format. Okay. So what is ln? ln is basically log base e. So it's ln log p by 1 minus p base e. Okay. So I can write it as p by 1 minus p is, if e goes to the RHS, it becomes exponential of w0 plus w1x. Okay. Now let's put 1 minus p in the RHS, that is bring it to the RHS like this. Okay. Then let's open this like this. Okay. And then let's bring this term to the RHS. Or maybe we could do another manipulation as well. Let's take out p common. So this would become like this, and this would become like this. Right? We are taking p common. So now this pp cancels, and in the LHS we are left with only 1. Like this. Okay. So now we have 1 plus e to the power w0 plus w1x. And here we have, so what I have done is brought this term to the LHS. Now p goes to the LHS and this term comes in the denominator. Like this. Now the last thing that we will do is divide the numerator as well as the denominator with the same quantity, which is e to the power w0 plus w1x. So this would be 1, and then we have, this would be if this comes in the denominator, so 1 by e to the power w0 plus w1x, it would be e to the power minus w0 plus w1x, and then we have 1 here. So it would be like this. Okay. So now if you see, your probability is this, and this is basically your logistic regression model. This is your logistic regression model, and this is called the sigmoid function. So basically what happens is your P is going to be in this way. So whatever your x is, your y will always be in the range 0 to 1, like this. So this is basically the sigmoid function. So whatever your x is, your y will always be in the range 0 to 1. So we started off with y is equals to b0 plus b1x or w0 plus w1x. But then what did we get? Y is equals to 1 by 1 plus e to the power minus 0 plus w1x. And minus is common for w0 and w1 both. Either you say it as 1 by 1 plus e to the power minus w0 plus w1x, or you say that it's minus w0 minus w1x. Okay. So this is basically the mathematics behind logistic regression. We call it as regression because the mathematics is derived from linear regression. Okay. And here now our answer will always be between 0 and 1. So this is about logistic regression. Let's talk about the error term also. So obviously this is our logistic regression, but we want to minimize our error to get our W0 and W1. In linear regression also we were doing the same thing. We knew what the model is. We had to minimize the error and then get our W0 and W1, and that once we have the W0 and W1, we would be getting the linear regression model. Here also we know that this is the model. We have to minimize the error, the cost function or the error function, and then figure out what our W0 and W1 are. And once we have that value, our logistic regression model is ready with us with like it's complete. So right now we don't know what W0 and W1 are. We have to minimize our cost function and get our W0 and W1. Okay, let's move ahead. So we talk about the loss function here. In linear regression, it was sum of square of errors, right? But here we don't have this loss function. The reason we don't have this loss function here is because there this was solvable to give us the global minima or the minimum error. But here this won't be solvable to help us it give us the minimum solution. So we have to modify our loss function. So our loss function would actually be, so for a particular point. So for a particular point, let me write. It's basically minus y actual log y predicted plus, or you can say minus only. Basically, you can take minus common, or here I'm not taking minus common. Okay. Minus 1 minus y actual log 1 minus y predicted. So if you have to take the minus common, it would become minus y actual log y predicted plus 1 minus y actual log 1 minus y predicted, like this. Okay. So basically your y actual will always be either 0 or 1. Your y predicted will be the probability, but your y actual will always be between 0 and 1. So for a particular point where the y actual is 1, what will we have? Minus 1 log y predicted minus 1 minus y actual. 1 minus y actual will be 1 minus 1, which is 0. So this term will go away. So we'll only have the loss as minus log y predicted. And when this is when y actual is 1. When y actual is 0, what will happen? Minus 0 log y predicted will become 0, and then we'll be left with minus 1 minus y actual log 1 minus y predicted, which means 1 minus 0 log 1 minus y predicted, which means 1 into log 1 minus y predicted. So what I'm trying to show you here is that both the terms won't remain. Either the first term will remain or the second term will remain. So either your loss would be this or your loss would be this. And then you have to add the losses for all the points and then try to minimize it. You have to add the losses for all the points and then try to minimize it. And this is solvable to give us the global minimum. And how will you write your y predicted? You will write it as 1 by 1 plus e to the power minus w0 plus w1x. So basically, you are going to add the losses for all the points and write the equation in terms of w0 plus w1x and then try to differentiate it and get the loss function. That mathematics is a bit complicated, so that's why we are not doing. But I have told you what the loss function is, and you have to solve the loss function, that is minimize it to give you the coefficients, to give you the W0 and W1. W0 is basically the intercept, W1 is called the coefficient. Okay, are we fine so far? Okay. So this was all about how we actually build our logistic regression model. We use the training data to find our W0 and W1, to find our intercept and the coefficients. And once we have the model ready, once we have minimized the error we on the training data, we will have our W0 and W1, and our model would become y is equals to 1 by 1 plus e to the power minus W0 plus W1x. And now we can test it on the testing data. Okay, let me see. Okay, I'll have to reload this. Sketch got hanged. So now we have built our model on the training data. It's now time to evaluate our model on the testing data. Let me open this again. Something went wrong. Let's just check. Otherwise, we'll move to the slides. Am I able to open anything else? Yeah, there's something wrong with the sketch. Let me close these and open. Okay, no worries. So we've completed till here. We have understood the loss function as well. And now we have to evaluate our model on the testing data. Okay. So now, first what we do is we create a confusion matrix. And from that, we are able to find out what our accuracy is, what precision is, what recall is. In classification, there are lots and lots of evaluation metrics. In linear regression or in regression, there were just four evaluation metrics: MSE, RMSE, R square, adjusted R square. MSE and RMSE were almost the same, and adjusted R square was just you can say, a optimization over R square. But in logistic regression, we'll have lots and lots of evaluation metrics, and these are not only there for logistic regression, but they are for any classification algorithm that we have, be it regression trees, be it decision trees, be it random forest, be it any classification technique. Okay, so let's move on to what confusion matrix is. Uh, Now we know there are two possible values for our y actual, which is 0 and 1, and we have two possible values for our y predicted, again, which are 0 and 1. Why there are only two values? Because we'll be getting the probabilities, but based on the threshold, we are going to make them as 0 and 1. Okay. One second, let me see. Okay. So now there are a few terms. There are a few terms that we have. Sketch. Somehow this does not open. Let's see if we can use something else. Okay. So now, yeah, I think this is fine. Yeah. So now what is the confusion matrix? Basically, as we discussed, there are two possible values of y actual and there are two possible values of y predicted in case of binary classification. So let's say for actual, we write it here. Actual could be y could be 0 or 1, that is the person was placed or unplaced actually, and predicted can also be 0 and 1. That is, finally, we predicted him to be placed or unplaced. Now, here we have four values A, B, C, D, four cells. Now, basically, there are four terms that we say true negatives, true positives, false negatives, false positives. Let's understand each one of them. So, the first one is true negative. So, what does true negative mean? True negative means the second term here will say what our prediction is. So, our prediction is negative. That is, prediction is negative or prediction is 0. And the first term will tell us whether our prediction is true or false. If our prediction is true, then the actual value is also true. If our prediction is false, then our and if we have a true here, then the actual value is also false. So basically, true tells us whatever the prediction is, your actual value is also the same thing. Whereas false will tell us whatever your prediction is, your actual value is going to be the opposite of it. Okay. So actual is going to be 0. So the second term tells us that, hey, the prediction is negative. The second term or the second letter tells us that the prediction is negative, and writing true will tell us that the actual value is also the same as prediction. So if the prediction is 0 and the actual is 0, then it's basically called as true negative. Okay. Now let's talk about true positives. So true positives mean first the second letter. Prediction is positive and prediction is positive. That means 1. Prediction is positive. And true means that whatever you are saying as the prediction, that's correct. So actual is also 1. So when the actual is 1 and the prediction is 1, it's basically true positive. Agreed? Now, let's talk about the next term. So here the prediction is negative, that is 0. And the prediction is false. That means whatever you have said as the prediction, the actual is opposite of it. So when the prediction is 0 and the actual is 1, it is called false negative. What is false positive? The prediction is 1 and false means that the actual is going to be opposite of it, that is 0. So prediction is 1 and the actual is 0, that is false positives. So here we will write the number of true negatives, here we'll write the number of false positives, here we'll write the number of false negatives, and here the number of true positives. What should we try to maximize? True negatives is something that a model is doing correctly. That is, it is able to make the right predictions. If the actual value is 0, it is able to make the prediction as 0. And here also, if the value is 1, it is able to make the right prediction. So basically, we should try to maximize our true negatives and true positives, whereas false negatives and false positives are actually errors. False positive is basically called a type 1 error, and this is called type 2 error. Okay, so now we know what are true negatives, false negatives, and true positives. Okay, okay. Now we've understood what our confusion matrix is. It basically summarizes the predictive results of our problem, of our classification model. If there are two categories, that is, we have y can only take 0 and 1, then we have a 2 cross 2 matrix. If there are, let's say, three categories, that y can take the value 0, 1, 2, then we'll have a 3 cross 3 matrix. So basically, it will depend on the number of unique values that our y can take. If the number of unique values that a y can take, or that is the number of categories are 4, then the confusion matrix would be 4 cross 4. Now, this was about confusion matrix. Now we use this confusion matrix or the true positives, true negatives, false positives, and false negative terms to actually get our evaluation matrix. And the first one is called accuracy. Okay, the first one is called accuracy. So accuracy basically means something that you are doing correctly divided by the total, right? Something that you are doing correctly divided by the total. So what are we doing correctly? Our model is able to get the true positives and the false positives, true positives and the true negatives correctly. True positive is something that was actually positive and the model also predicted it as positive. And what are true negatives? They were negatives, the points were negatives actually, and our model also predicted them as negatives. So these are the two things that a model is doing correctly divided by the total, which is true positives plus true negatives plus false positives plus false negatives. Now, accuracy should be high or low. It should be high. It should be as close to 1 as possible. Okay. Another evaluation matrix that we will have. So this is the first one. Now the next one that we have is called recall. The next one is recall. So it is defined as the ratio of total number of correctly classified positive classes. Correctly classified positive classes divided by the total number of positive classes. Okay. So correctly classified positive classes means they are actually also positives and they were predicted also as positives. That means true positives is the numerator. And what is the total number of positive classes? The total number of positive classes means actually how many positive classes were there. Let's see. Out of them, actually how many of them are positive? So true positives means predicted as positive, actually also positive. True negative means predicted as 0, actually also 0. False positive means predicted as 1, but actually they are 0. False negative means predicted as 0, but actually are 1. So how many of them are actually positive classes? And true positives and false negatives, right? So total actual positive classes would be true positives plus false negatives. And this is basically your recall. And recall should also be as close to 1 because in the denominator we have false negatives which we want to minimize as much as possible. Okay, so we understood what accuracy is, then we understood what recall is. Now we'll go to the next one, which is called precision. So these are all the evaluation metrics that are used for classification models. Let's move to precision. So precision is defined as total number of correctly classified positive classes. So correctly classified positive classes divided by the total number of predicted positives. total number of predicted positives. So in recall, what we were doing, we had total number of correctly classified positive classes divided by the total number of positive classes. That means out of all the positive classes, how many our model was able to classify correctly. Whereas precision is the total number of correctly classified positive classes divided by the total number of predicted positive classes. So precision means that is out of all the predicted positives, how many of them were actually positives. Out of all the total number of predicted positive classes, how many of them were actually positive classes? Okay. So what is correctly classified positive classes? The numerator remains the same, which is true positives, and divided by the total number of predicted positives. That is, the prediction should be positive. In TP, the prediction is positive, and in FP also the prediction is positive. Again, this should also be high, as close to 1 as possible. So we discussed about accuracy, then we discussed about recall, and then we discussed about precision. Accuracy is what? Accuracy is what is your model doing correctly out of the total number of uh, testing points, or how many points your model is able to figure out or classify correctly out of the total number of testing points. Recall is basically the ratio of the total number of correctly classified positive classes divided by the total number of positive classes. And what is precision? Precision is the ratio of total number of correctly classified positive classes divided by the total number of predicted positives. Now, there is another evaluation matrix which is called F-score. So, what is this F-score? It basically combines our precision and recall. We want our precision to also be high and our recall also to be high. And one model in which precision is very low and recall is very high, it is not a good model. We want our precision and recall both to be high. So that's why we combine both of these evaluation metrics using another evaluation matrix which is called F-score, which is the harmonic mean of precision and recall. It is the harmonic mean of precision and recall. So let me talk about if there are two numbers A and B, then the arithmetic mean is A plus B by 2, whereas the harmonic mean is 2 by 1 by A plus 1 by B, which is 2 by A plus B by AB, which is 2AB by A plus B. Okay, so let me increase the size width. So basically, F score basically means the harmonic mean of precision and recall. So 2PR, 2 into precision into recall by precision plus recall. This is what our F score is. Okay. Now, why are we saying harmonic mean and not the arithmetic mean? Because what happens is, if let's say our precision is 0 and our recall is 1, we don't want this. This is not a good model. Our precision and recall both should be high. So if you see your arithmetic mean would give P plus R by 2, which is 0.5, which suggests that this model is decent. Whereas harmonic mean will suggest 2 into P into R by P plus R, which is 2 into 0 into 1 by 0 plus 1. Since we have a 0 in the numerator, harmonic mean will become 0. So this suggests that it's not a good model, whereas this suggests it's a decent model. That's why we go for harmonic mean, because we want to have both the precision and recall to be high. Whenever precision and recall both are high, then only our F score will be high. Even if one of them is low, then our F score is going to be low. So we want both of them to be high, and then only our harmonic mean will be high. And that's why when precision and recall both are high, then only our F score is high. So if we have high F score, we can say precision and recall both are high. Okay, that's why we are taking harmonic mean and not the arithmetic mean, because harmonic mean, even if one of them is low, it is going to punish it, and the value will be less, whereas arithmetic mean will even give us a decent value there. So that was about F score. Now we have one more evaluation matrix which is called Specificity. Specificity. Now, what is this? It is basically the proportion of actual negatives that are correctly identified. It's basically out of all the actual negatives, how many of them are correctly identified. So, which are correctly identified? Obviously, true negatives are the ones which are correctly identified as negatives, and they are actually negatives also. So, and how many actual negatives we have? True negatives are basically actually also negatives. And if you see your false positives, they are also actually negatives, right? Because they are predicted as positives, but the prediction is wrong, and the actual is basically negative. So that's why specificity is true negatives divided by the actual negatives, which is true negatives by true negatives plus false positives. I can show you. TP means predicted as 1, actual as 1. TN means predicted as 1, actual, predicted as 0, actual as 0. False positives. Predicted as 1, actual is 0. Then false negative means predicted as 0, actual as 1. So we want actual negatives, these two. So that's why I am writing Tn plus Fp. Okay. So this is basically all about our evaluation metrics. These are not all, but these are the few important ones. Precision, recall, that is accuracy, and then F score and specificity. So we have studied 5 so far: classification accuracy, recall, precision, F score, and specificity. Okay. Now we will understand the last evaluation matrix, which is actually AUC ROC curve. But for that, we will understand one more thing, which is basically some terms. So let me tell you those terms. So the first term is TPR, true positive rate. So how do you figure out what your TPR is? Since you have TP written, just write it in the numerator. And what are true positives actually? They are positives, right? So the denominator would be whatever they are actually, that is total positives. Now, let me just write it here. TP means predicted as 1, actual is also 1. FP means predicted as 1, actual is 0. FN means predicted as 0, actual is 1. FP means predicted as 1. Okay, FP is done. Then I have to go with TN. TN means predicted as 0, actual also 0, right? I've written it so that it's easier for you to tell me what total positives are. Total actual positives means this one and this one, right? So it will be TP by TP plus FN, right? And if you remember, this is actually your recall also. Recall is also called as sensitivity. Okay, recall is also called as sensitivity. So TPR is basically out of all the total positives, how many your model was able to identify correctly. Obviously, it should be high. Now, what is FPR? FPR means you have FP in the numerator, put it here. And what is FP? FP means predicted as 1, actual as 0. So basically, they are 0, actually negatives. So basically, FP by the total negatives that you have. So basically it will be FP by total negatives. Total negatives means this one and this one. Actual total negatives, that is FP and TN. So basically out of the total actual negatives, how many your model was able to identify incorrectly. And this should be low because whatever your model is identifying incorrectly should be low. Okay. Now the next term. So we did TPR, we did FPR. Now let's do the next term, which is TNR. What is TNR? Basically, true negatives, again, Tn will come in the numerator and the denominator would be total negatives. What are true negatives? True negatives are basically predicted as negatives and they're actually negatives also. So basically total negatives. So What are total actual negatives? So actual should be 0, that is FP and TM. So basically out of all the total negatives, how many your model was able to identify correctly as negatives? Again, this should be high. And if you see this TNR is actually your specificity. Specificity. Okay. Now, moving on to the next one, which is FNR, the last one. So FNR is what false negatives divided by what are false negatives. They are predicted as negatives, but they are actually positives. So divided by the total positives. So what are total positives? Total positives would include TP and FN. Actual one, TP and FN. So out of all the total positives, how many your model was able to identify incorrectly? And this should be low because your model should do incorrect things less and correct things more. Okay. So this was about the four terms TPR, TNR, FPR, and FNR. Now, how is it related to AUC ROC curve? So AUC ROC is basically the last evaluation metrics that we have, and it is one of the most important evaluation metrics for checking any model's performance. And it is basically written as AUC ROC. You can write it as AU ROC also. So basically, AUC ROC is what? Area under the curve, receiver operating characteristics. And this is the graph that we make between TPR and FPR. This is the graph that we make between TPR and FPR for different thresholds. If you change the thresholds, your TPR and FPR are going to vary, and you're going to draw a plot between TPR and FPR for different thresholds. So let's say for one threshold it was this, for another threshold it was this, for another threshold it was this, and for another threshold it was this. What I mean to say here is that for one particular threshold, TPR was A and FPR was B. So this is the first point. Similarly, for different threshold, your TPR was something and FPR was something, and the point would be here, then here. So basically, you have to draw a line between them, and basically, not a line, draw a curve combining all the points. So this is basically the area under the curve of TPR versus FPR graph. Okay, and basically this AUC should be high because this AUC, okay, this is the graph. Now, what is the area under the curve? This is the graph, right? Now, what is the area under the curve? The area under the curve is how much does this curve make with the horizontal x-axis. So basically, this is the area under the curve. How much this curve makes with the horizontal x-axis. That is the area under the curve, and this should be high. So the area under the curve is the measure of the ability of a classifier to distinguish between the classes. Okay, so this area under the curve should be high and it should be close to 1. Okay, so the higher the AUC, better the performance of our model is in distinguishing between the positive and the negative classes. So obviously, there is mathematical proof to it why the AUC should be high, but for now, we are restricting ourselves to only the logic. The logic is that if the AUC is high, then our model's performance is great. And what is AUC? Area under the curve of this ROC curve, area under the curve that this curve makes with the horizontal x-axis. The area that this curve makes with the horizontal x-axis. And the max could be 1 because your TPR will also be from 0 to 1 and your FPR will also be from 0 to 1. So max the area that we can have is 1. And when can we have that? So if this is TPR and this is FPR, then the max could be like this. Here we have 0, here we have 1, and here also we have 1. Okay, so AUC is basically the area under the curve and area under the curve that your ROC curve or your TPR versus FPR curve makes with the horizontal x-axis. Okay, And basically, what is this ROC, receiver operating characteristics? It is basically the graph between TPR versus FPR at different thresholds. Let me explain you why we will have different TPR and different FPR at different thresholds. So let's say the actual values that we have, actual Y values are these 0, 1, 0, 1, and so on. And the probabilities that we got were out of our logistic regression model were 0.98, 0.67, 0.58, 0.78, and so on. If we take the threshold to be zero point 0.6, any value which is greater than equals to zero point 0.6 will be treated as prediction 1, otherwise it will be treated as 0. So 0.98 will be predicted as 1. 0.67 will also be predicted as 1. But 0.58, which is less than zero point 0.6 will be predicted as 0. 0.78 predicted as 1, 0.85 predicted as 1, 0.86 predicted as 1, 0.79 predicted as 1, and so on. If you see this, so basically you have some TPR, FPR, TNR, and FNR. But when you change the threshold to be 0.7, 0.98 will be predicted as 1 as usual, but 0.67, which was predicted as 1 when the threshold was zero point 0.6, will now be predicted as 0 when the threshold is 0.7. 0.58 will also be predicted as 0.7. Will be predicted as 0. 0.78 will be predicted as 1 because it's greater than the threshold. So if you see, the number of true positives, true negatives, false positives, and false negatives would vary depending on the threshold. So that's why your TPR, FPR, TNR, and FNR will vary. For example, if you see the last one also, when the threshold is 0.8, 0.98 will be treated as 1, but 0.67, 0.58, 0.78 will be treated as 0. So this 0.78, which was predicted as 1 when the threshold was 0.6 and 0.7, is now predicted as 0 when the threshold is 0.8. So based on the threshold, the TPR, TNR, FPR, and FNR are going to vary, and we have to draw the graph between the TPR and the FPR at different thresholds. And that's what the ROC curve is. And what is AUC? AUC is area under that curve, and it should be high, because if higher the AUC, better is the model's performance. Okay. So those are the evaluation metrics that we have. We started off with accuracy, then we went to precision, recall, specificity, F score, and then AUC ROC curve. Okay. So that's all the evaluation metrics we have. So first we build the model on the training data, figure out and have our loss function, try to get the best coefficients. That is basically build your model on the training data and then evaluate it on the testing data. All of these evaluation metrics are important. It depends on you which evaluation metrics you want to select. Generally, people go for F score and AUC ROC. Because F score is the combination of precision and recall, and AUC ROC is one of the common ones which compares the TPR and the FPR. You can go for accuracy also, but it can be used only for the balanced data. What does balanced data means? When you have equal number of